Okay. Hi everyone. So good afternoon all. Good afternoon. So first let me know whether audio and video are clear. Yes. So let me know whether audio and video everything is clear here. Is everything clear? Yes. Okay. Okay. So I hope it is clear. I hope audio and video everything is clear here. I hope audio and video everything is clear. Right. Sayan Devnath. Yes. Okay. Okay. So we are dealing with the subject electromagnetics, and the topic that we have discussed in the previous session. The topic that we have discussed in the previous session is nothing but what here? Is nothing but divergence theorem. Yes or no? So we have discussed in the previous session divergence theorem. So just I am revising here. So in the previous session we have discussed about divergence theorem, right? Okay. So what I have told here? If you consider any closed surface here, so if suppose some field is leaving this closed surface, okay, so how much of this field is leaving this closed surface is called as what? Is called as flux leaving the closed surface. So how to represent the flux leaving the closed surface here? If you consider a small differential area, dA bar, on this closed surface, yes or no? Okay. So then if you want to determine how much of the field is penetrating through this small differential area, then you have to represent that as what here? F bar dot dA bar. Let the vector field be F bar. We want to determine how much of this vector field is going to penetrate through this small differential area dA bar. So if you want to do that, what you have to do? You have to do F bar dot dA bar. So this is going to give you the flux through this small differential area dA bar. Now if you want the total flux, that is leaving through this closed surface, then what you have to do? You have to integrate throughout what? Throughout the closed surface. That means at this location you are trying to determine how much of the given vector field is penetrating through this small differential area. Similarly, you can consider some other differential area here, and here also you try to determine how much of the field that is penetrating through this small differential area. So like that, at each and every location on the surface of this closed surface, at each and every location you have to determine F bar dot dA bar, and you have to add up all those throughout this closed surface. So that is going to give you what? That is going to give you the flux that is leaving the closed surface, or we can say how much of the given vector field is penetrating or leaving or passing through this closed surface. Right. Okay. So in the previous session I have told that this is equivalent to what? This is equivalent to what here? See, some vector field is leaving this closed surface, means inside this closed surface there must be what? There must be some source of this field. If there is no source here, inside the closed surface, then there will be no field. Some field is coming out of closed surface, means inside that closed surface some source of that field must be present. Yes or no? Now let us assume some different sources, are present inside the closed surface. Yes or no? Inside the closed surface, or I can say some sources are present within this volume. So this volume is enclosed by this closed surface, right? Okay. So now So now let us consider this is one point source, this is point source, this is point source, this is point source, like that. Okay, so these sources are distributed throughout the volume that is enclosed by this closed surface. Now what we have done here, we have determined how much of the field that is leaving from each and every point source, how much of the field that is leaving from each and every point source. So how much of the field that is leaving from each and every point source is nothing but what? Is nothing but the divergence at that point or not? Yes or no? If you want to determine how much of the field that is leaving from this point, then you have to determine the divergence at this point, right? Okay, so like that, if you calculate how much of the field that is leaving from each and every point, how much of the field that is leaving from each and every point source, then if you add up all those, what you are going to get? You are going to get how much of the field that is leaving the closed surface or not? Yes or no? If you calculate how much of the field that is leaving from each and every point source within the volume, so if you add up all those, finally you are going to get how much of the vector field is leaving the closed surface. Yes or no here? So if you want to determine how much of the field that is leaving from any point, that is nothing but what? That is nothing but divergence. Divergence is a measure of what? How much of the field that is leaving from a given point. So that means you have to calculate the divergence at each and every location, throughout the volume, and you have to add up all those divergences throughout the volume. So if you add up all those divergences throughout the volume, then what you are going to get? You are going to get how much of the field that is leaving the closed surface, or I can say the flux that is leaving the closed surface. Yes or no? So this is equivalent to what here? The flux leaving the closed surface is also equivalent to what? Is also equivalent to divergence of F bar. If you consider a small differential volume here, like this, okay, so if you add up all the divergences, over this small differential volume dV, you can represent that as what here? Divergence of F bar into dV. So this will give you the addition of divergences over this small differential volume dV. Now if you want the total, if you want to add all the divergences throughout this volume here, then what you have to do? You have to integrate throughout the volume. Yes or no? So summation of all the divergences at each and every point throughout the volume is equivalent to what? Is equivalent to the flux that is leaving the closed surface. So both are same here, So this is what we have discussed in the previous session. So the flux leaving any closed surface, you can represent either with this expression or you can represent with this expression. Right. So in terms of closed surface you can represent, or in terms of volume you can represent in this manner. Okay. So now then what we have done here, see the purpose of this divergence theorem. Is what here? The purpose of this divergence theorem is mathematical calculations can be very much simplified. Here if you use this divergence theorem. Right. Okay. See, if you want to determine the flux through any closed surface, you can use either this expression or you can use this expression. Right. So in most of the problems here, if you use this expression, the problem will get very much simplified. Okay, when compared to this one, if you use this expression, the problems will be very much simplified here in general. Okay. Okay, so in order to justify this statement, I have given one example here. So I will just revise that example here. What I have given. So I have given a vector field here. F bar is equal to x ax cap plus y ay cap plus z az cap. Okay, so then I ask you to determine the flux through a closed surface, that encloses a volume which is given by x is varying from -1 to +1, y is varying from -1 to +1, z is varying from -1 to +1. So this is the problem I have given here. So I have given roughly here. So f bar, I have given some vector field. Now I am asking to determine how I am asking to determine the flux through closed surface, the flux through closed surface that encloses a volume, which is given by what? Which is given by x lying between -1 to +1, y is ranging between -1 to +1, z is ranging between -1 to +1. So this is the volume they have given here. This is the volume they have given. So this volume is going to have what? This volume is going to have some boundaries or not? Yes or no here? So whenever you are specifying a region or volume, so that volume must have what? That volume must have boundaries. Yes or no? Now here we know that since x, y and z are variables, this volume is going to represent what? Volume of a cube. Volume of a cube. Yes or no? So that volume of a cube is bounded by how many surfaces here? Whenever you consider a cube here, if you consider a cube, okay, so that cube is going to enclose some volume. So that volume is bounded by the surfaces of the cube or not? Yes or no? So this cube is going to have how many surfaces? 6 surfaces or not? Yes or no? So what are those surfaces here? What are those surfaces? This one is x is equal to -1 surface, and this one is x is equal to +1 surface. So that means you are having x equal to -1 surface and x is equal to +1 surface, right? So these are the two sides of a cube here. These are the two sides of a cube. Next, this represents two surfaces of a cube. Next, y equal to -1, y equal to -1 and y equal to +1 will represent what? Another two surfaces. And here z is equal to -1 and z is equal to +1 will represent what? Will represent another two surfaces. So that means you are going to have the cube like this. Yes or no? Okay. We have already discussed here this one, just I am revising that. Okay, so here I have considered this axis as x axis, this axis as y axis, and let us assume z axis is coming out of the board. Right? Okay, so this is the cube here, this is the cube. So this is the volume of the cube. This volume of the cube is bounded by these boundaries, that is these 6 surfaces of the cube. Yes or no? See, closed surface will always enclose what? Will always enclose the volume, right? Okay. So x is equal to -1. So this surface is nothing but what? X is equal to -1 surface, and this is nothing but x is equal to +1 surface. See here, x is equal to -1 is what? X equal to constant plane or not? X equal to constant plane means only y and z are variables and x value must be constant. That constant value is -1. Understood? Now if you consider this is x axis, this is y axis, z axis is coming out of the board. So x is equal to constant plane is nothing but what? Is nothing but yz plane or not? Yes or no here? Is nothing but yz plane. So here it is parallel to what? It is parallel to yz plane. So x is equal to -1 and x is equal to 1 are parallel to what? Are parallel to yz planes. Right? Okay. Next, similarly, you are going to have what? You are going to have y equal to -1 and y equal to +1. Y equal to -1 and y equal to +1. So these are y equal to constant planes here. So y equal to constant planes must be parallel to what? Must be parallel to this zx plane or not? Yes or no? Y equal to constant plane represents what? Represents zx plane. Right? So this is the zx plane located at y equal to -1, and this is another zx plane that is located at what? Located at y equal to +1. Right? So similarly you are going to have front surface. So front surface is z is equal to 1, and back side you are going to have another surface, that is z is equal to -1. Right? So these are the 6 surfaces of what? 6 surfaces of the cube. Right? Yes or no here? Yes. 6 surfaces of the cube. Now they are saying that they have given that some vector field. They have given some vector field x ax cap plus y ay cap plus z az cap, and they are asking to determine how much of the flux that is leaving this closed surface. So now how to determine here? So we can determine the flux through any closed surface. We can represent in this manner or not? Closed surface integral f bar dot dA bar. Okay, so if you want to expand this one here, if you want to expand this one, or if you want to determine the flux through any closed surface by using this expression, in this problem. So how you have to determine here? You have to determine the flux that is leaving through this surface, the flux that is leaving through this surface, the flux that is leaving through this surface, and the flux that is leaving through this surface, and also you have to determine the flux leaving through z equal to 1 surface and the flux leaving through z equal to minus 1 surface. Yes or no? So that means you have to determine the flux, determine the flux through first surface. Let us say this is 1, this is 2, and this is 3, and this is 4. Front surface is 5, back surface is 6. Let us assume. Okay, so you have to determine the flux through the first surface plus the flux through second surface plus the flux through third surface plus the flux through fourth surface, right, plus the flux through fifth surface plus the flux through sixth surface, sixth surface. So you have to calculate the flux through each and every surface, and you have to add up all this here. You have to add up all this in order to get the flux through all the 6 surfaces, or I can say the flux that is leaving through the closed surface, right? Okay, so this is somewhat lengthy procedure here. Yes or no? Okay. So instead of following this procedure, so we can use another expression. By using divergence theorem, we can represent this closed surface integral f bar dot dA bar as what here? As we can represent it as what? We can represent it as triple integral divergence of f bar into dV. Yes or no here? So whether you solve the problem by using this expression or this expression, both must be what? Both must give you the same result. Yes or no? According to divergence theorem, this one and this one both must be same. Okay, so we have calculated the divergence of the given vector field and substituted here, and here substituted the ranges of x, y and z. We got within 1 or 2 steps, we got the answer. Yes or no here? So we got, we have already checked here in the previous session itself. We have checked for this problem. We got what? We got 24 units here. 24 units. Whether you solve the problem by using this expression or if you solve the problem by using this expression also, you got what here? Finally, the answer. The answer we got here also 24 units here. 24 units. So whether you solve the problem by using this expression or this expression, the result we got is same, that is 24 units. Yes. Yes. Okay. So I hope it is clear here. I hope it is crystal clear. Right. So you can go through that problem here, or you can solve here. I have given f bar. Okay, so you have to determine the flux through each and every surface by using this relation, or you can determine the flux through the given surface by using this relation. So in both the cases, you have to get what? You have to get the same answer. Right? Okay. So I hope it is crystal clear. Right? Okay. So this is what we have done in the previous session. Now, in this session, first we will start. See, in the previous sessions also, what we have done is, before learning about divergence, before studying about divergence, we have studied about what? We have studied about flux. So here also, before studying about curl, we have to understand what do you mean by circulation of the vector field around any closed loop. So here you have to study the concept of circulation. There you have studied the concept of flux before divergence. Here before curl, you have to study the concept of circulation. Right? Okay. So first we will see that here. Listen. So we will study about circulation of the vector field, circulation of the vector field around any closed loop, circulation of vector field around any closed loop. Circulation of vector field around any closed loop. So how to determine this one? See here. See. See, what do you mean by circulation of the vector field around any closed loop here? What do you mean by this statement? What do you mean by this one? Circulation of vector field around any closed loop. So it means it is a measure of, it is a measure of, see, I am explaining all the definitions in the same manner here. Almost I am using the same terminology so that you can easily remember all those definitions, right? So it is a measure of, how much of the given vector field, how much of the given vector field, how much of the given vector field is aligned around a given closed loop, okay. So that means what here? So whenever I am talking, I am saying like circulation of vector field around any closed loop, it means it is a measure of what? It is a measure of how much of the given vector field, is aligned around a given closed loop. So suppose you are having some vector field here, some vector field is distributed here. Now you want to determine how much of this vector field is aligned around a given closed loop. How much of this vector field is aligned around that given closed loop. Okay, so that's what you want to determine. Okay, so that is called as circulation of the vector field around any closed loop here. Okay, so we will see how to represent this mathematically. So for that we are going to develop it step by step here, step by step. So as we have done while learning flux, the same procedure we are going to follow here also. Okay, in order to learn the concept of this circulation. Now see here. So I am taking case 1 here. Okay, so here I am considering a vector field. So let us say this vector field is f bar. Now here I am considering some length here, some length L bar. Right. So this is case 1. Next case 2. So here I am considering the same length here. So here I am considering length L bar, right? So here I am considering the length L bar, and here I am considering the vector field. In this direction. Right. Okay. Next case 3. So this is length L bar, and here I am considering the vector field in this direction. See, if you would have attended or if you have learned about flux, okay, then it is going to be very simple here, right? Okay. So F bar, L bar. So these are the 3 cases I have considered here. Now tell me, see here. If I ask you a question, how much of this given vector field, is aligned along this given line? How much of the given vector field is aligned along this given line? Tell me here. See here, if you observe, whatever the field they have given here, the total field is aligned along this given line or not? Yes or no? Now here in this case, the angle between F bar and L bar is nothing but what here? F bar and L bar is nothing but what? 0 degrees or not? Yes or no? The direction of the vector field and the direction of length both are pointing in the same direction. So here the angle is 0 degrees between F bar and L bar. Right. So here the total field is aligned along the given line. So that means you are going to get the total field is aligned along the given line here. Right. Okay. When theta equal to 0 degrees. Now if you observe here, if you observe this one, so here the vector field is pointing in this direction. The vector field is pointing in this direction, that is perpendicular to what? Perpendicular to this length. Now in this case the angle between F bar and L bar, the angle between F bar and L bar is how much here? Theta is equal to what? Theta is equal to 90 degrees. Theta equal to 90 degrees. Now in this case, how much of the given vector field, is aligned along this given line here? How much of the given vector field is aligned along this given line? Tell me here. How much of the given vector field is aligned along this given line? Now here in this case no vector field is aligned along the given line. There will be no vector field that is aligned along the given line. Yes or no? So that means here you are going to get here you are going to get no field is aligned along the given line. Right. Okay. Next. If you observe third case here, now here the vector field is pointing like this, yes or no, and the length is pointing in this direction, yes or no, L bar is pointing in this direction. Now here if I ask you how much of the vector field is aligned along the given line, so for that what you have to do, so here this is F bar here, this is F bar, yes or no, this F bar is neither parallel to L bar nor perpendicular to L bar, so I can resolve this vector field into two components. One is what? One is parallel to L bar and another one is what? Perpendicular to L bar. So one is parallel to L bar and another one is what? Perpendicular to L bar. Now in this case only a part of the field, yes or no, only a part of the field is aligned along this length. Yes or no here? So only the component of the field that is parallel to what? That is parallel to L bar is aligned along the given line. Yes or no? The component that is perpendicular to L bar is not aligned along the given line. Right. So now here theta is lying between what here? Theta is lying between 0 degrees and 90 degrees. Yes or no? So theta is lying between 0 and 90. Now here, see here. So that means the field that is aligned along a given line, is depending upon what here? Is depending upon the angle between F bar and L bar or not. It is depending upon the angle between F bar and L bar. So whenever theta is equal to 0 degrees, you are having what? Maximum alignment of the field along the given line. So whenever F bar and L bar are perpendicular to one another, you are having no field is aligned along the given line. Whenever F bar and L bar are making some angle between 0 and 90 degrees. In this case, only a part of the field or only a component of the field that is parallel to L bar is aligned along the given line. Yes or no? So that means the field that is aligned along the given line is depending upon what? Is depending upon angle between F bar and L bar. So whenever theta equal to 0 degrees, you are getting maximum value. Whenever theta equal to 90 degrees, you are getting minimum value, or you are getting what? You are getting zero value. And whenever theta lying between 0 and 90 degrees, now here you are getting lies between what? Lies between here the field that is aligned along the given line lies between what? Lies between minimum and maximum values. Right? Yes or no? And also on what parameters it is going to depend upon here? If suppose now if I decrease the length here, if I consider only this part of the length here, okay, so now if I try to determine the field that is aligned only along this line, only this part of the line if I consider, then the field that is aligned along this line is also going to reduce or not? Yes or no here? Yes or no? So what portion of the field is aligned along this line, So if length is reduced, then the field, the portion of the field that is aligned along this line is also going to reduce, Yes or no? Similarly, if I increase the strength of the field, that means if I increase the strength of field here, that is I am increasing the number of field lines, in this manner. So whenever I increase the strength of the field, then what will happen here? So the field that is aligned, along this given line is also going to increase. Yes or no? Okay, the field that is aligned along this given line is also going to increase. So that means the field that is aligned along a given line is depending upon what? Is depending upon the strength of F bar, or I can say magnitude of F bar, and also it is depending upon what? Magnitude of L bar, and also it is depending upon what? It is depending upon the angle between F bar and L bar. So whenever theta equal to 0, that means whenever F bar and L bar are pointing in the same direction, you are getting maximum value, and whenever F bar and L bar are perpendicular to one another, you are getting what? You are getting 0 value. And if it is lying between 0 and 90 degrees, you are getting the value between minimum and maximum, right? So which mathematical operation will satisfy all these conditions here? See, the field that is aligned along a given line is depending upon the angle between F bar and L bar, and whenever the angle is equal to 0, you are having maximum. That means whenever the two vector quantities are pointing in the same direction, you are getting maximum value. Whenever these two vector quantities are perpendicular to one another, you are getting 0 value, and the value is going to lie between minimum and maximum if the angle between them is lying between 0 and 90 degrees. So which mathematical operation will satisfy all these conditions? And also it is depending upon what? The magnitude of F bar and the magnitude of L bar. Okay, so it is depending upon magnitude of F bar, magnitude of L bar, and the angle between what? Angle between F bar and L bar. Okay, so which mathematical operation will satisfy all these conditions here? Which mathematical operation will satisfy all these conditions? That is nothing but what? That is nothing but dot product or not? Yes or no here? That is nothing but dot product between F bar and L bar, right? So the field, the amount of field, or the field that is aligned along a given line, can be represented by what here? Can be represented by F bar dot what? F bar dot L bar. So that is equal to what? That is equal to magnitude of F bar into magnitude of L bar into cos theta. Okay, so if you observe, it is depending upon what? It is depending upon magnitude of F bar vector field and magnitude of L bar, and also it is depending upon what? And also it is depending upon the angle between F bar and L bar. So when theta equal to 0, you are going to have the maximum alignment of the field. When theta equal to 90, you are having 0 alignment of the field. So if theta lying between 0 and 90, then the field that is aligned along the given line is going to lie between minimum and maximum value. Right. So in this manner, you have to represent what here? You have to represent the field that is aligned along a given line here. The field that is aligned along a given line. Right. Okay. So is this one clear here? Is it clear? Yes or no here? Is this clear? Respond here. So I am waiting for your response. So if it is clear, we will move further. Yes, give some comments in chat box here whether it is clear or not. Yes or no? Dev Sharma, Akash Chauhan, Harry, Sonu. Yes. Okay. So I hope it is crystal clear here. I hope it is crystal clear. Now see here. So now if I consider only a small differential length here, if I consider only a small differential length, Let us assume I am considering only a small differential length. That differential length I am representing with dl bar here. I have considered only a small differential length dl bar, right? Then if I ask you to determine what is the field that is aligned along this small differential length dl, what is the field that is aligned along this small differential length dl, then what you have to do here, the field that is aligned along a small differential length dl, I can represent it as what? I can represent it as f bar dot what? F bar dot dl bar. So this is the field that is aligned along what? That is aligned along a small differential length dl bar, right? Okay, now if I want to determine the field that is aligned along this total length here, if I want to determine the field that is aligned along this total length, then what I have to do? So this is the field that is aligned over a small differential length dl bar. If you want to determine the field that is aligned along the total length, then what you have to do? You have to integrate. Yes or no? You have to integrate throughout the line. Yes or no here? So this represents, this is the general representation here. This is the general representation of the field that is aligned along a given line here. So this is the general representation of the field that is aligned along a given line, along a given line, right? So this is the general representation. Of the field that is aligned along a given line. Okay. Now if suppose f bar is constant with respect to this integration variable here. If f bar is constant with respect to this integration variable, then you can take this f bar out of the integration. In that case you can write f bar dot what? F bar dot dl bar. So you are going to get what? You are going to get simply f bar dot what? F bar dot L bar. Yes or no? Okay. So whenever f bar is constant with respect to the integration, then you can directly write it as what? F bar dot L bar. So when you can write it as f bar dot L bar here, whenever f bar is constant with respect to what? With respect to integration variable. So this one you can write when f bar is constant, with respect to what? With respect to integration variable. Whenever it is constant with respect to integration variable, right? Okay. So when f bar is constant with respect to integration variable, so then in that case you can represent directly what? The field aligned along the given line, you can represent directly as f bar dot L bar. Otherwise, this is the general representation here. This is the general representation. This one. So this one is the general representation. Okay. So wait. So this is the general representation here. This is the general representation. Right. Okay. Yeah. So now see here. If you are having the vector field like this, if you are having some vector field like this, right? So if you are having some vector field like this, now you want to determine how much of this vector field is aligned around this closed loop. Now this is the vector field here, this is the vector field you are having. Now you want to determine how much of this vector field is aligned around this closed loop, Okay, so then in that case, how to represent mathematically this one here? So I will consider a small differential length here. dl bar. So then the field that is aligned along this small differential length, I can represent it as what? I can represent it as f bar dot what? F bar dot dl bar. Now I want to determine how much of this given vector field is aligned around this closed loop. how much of this given vector field is aligned around this closed loop. Then what you have to do? You have to add up f bar dot dl bar at each and every location around this closed loop. Yes or no? So that means you have to integrate throughout this closed loop. You have to integrate f bar dot dl bar throughout this closed loop. Yes or no? So this represents the field that is aligned around this closed loop. How much of the field is aligned around this given closed loop? Yes or no? Okay. So this is nothing but what here? This is going to give you how much of the field. This is going to give you how much of the field, how much of the given vector field, how much of the given vector field is aligned. How much of the given vector field is aligned around a given closed loop, around a given closed loop. See, first try to understand the concept here. Okay, so then then we can solve different problems so that you can easily understand further. Okay, so it is going to give you what? How much of the given vector field is aligned around a given closed loop. So initially I have given one definition here. See here. So what do you mean by circulation of the vector field around any closed loop here? Circulation of vector field around any closed loop is nothing but what? It is a measure of what? It is a measure of how much of the given vector field is aligned around a given closed loop. So here, so that means here this closed loop integral f bar dot dl bar is nothing but what? Is nothing but how much of the given vector field, is aligned around a given closed loop. That means this term, this expression, we can call it as what? We can call it as circulation of what? Circulation of vector field. This one we call it as what here? Circulation of vector field around, circulation of vector field, right? Circulation of vector field around any closed loop. Circulation of vector field around any closed loop. Okay, right? So if you determine how much of the given vector field aligned around any given closed loop, that is nothing but circulation of the vector field around any closed loop. So this is the way, this is the mathematical way to represent what? To represent the circulation of the vector field around any closed loop here, around any closed loop, right? Yes, here, is it clear? Yes or no? Is it clear here? So I hope it is crystal clear here. I hope it is crystal clear, right? So circulation of vector field around any closed loop you have to represent in this manner. Closed loop integral f bar dot dl bar. This represents the circulation of vector field around any given closed loop, right? Okay. Okay. Yes. Okay, so I hope it is crystal clear here. I hope it is crystal clear, right? Next here, next. See here. Now we will take one small example here. We will take one small example and try to determine the circulation of the vector field around that closed loop, around that closed loop. Okay, so now we will take one example here. We will take one example. So let us take this example. Okay, so let's say f bar is equal to x ax cap plus y ay cap. Let's say f bar is equal to x ax cap plus y ay cap. Then determine the circulation of vector field. Then determine the circulation of vector field, the circulation of vector field f bar around the closed loop, given in the following figure. given in the following figure. Okay, given in the following figure. So you have to determine, they have given F bar and they are asking to determine the circulation of vector field, the circulation of vector field around the closed loop, that is given in the following figure. So they have given the closed loop in the following figure here. So around that closed loop you have to determine how much of the field is aligned around that closed loop, or you have to determine the circulation of the vector field around that closed loop here, around that closed loop. Okay, so here this is the figure they have given here, this is the figure they have given, right? See here. So they have given, this is x-axis and this is y-axis, right? Okay, so they have given this closed loop here, they have given this closed loop. So this is the closed loop they have given here. So I am enclosing this closed loop in anti-clockwise direction like this, right? Okay, so here the vector field, F bar is equal to x ax cap plus y ay cap is present. Some vector field F bar that is varying as x ax cap plus y ay cap is present in this region, Now you want to determine how much of this vector field is aligned around this closed loop, So here they have given this point as 0, 0, and this point is 1, 0, and this point is 0, 1, and this point is 1, 1. Right? Okay, so this is the closed loop they have given and this is the vector field they have given. So this vector field is present in this region. Now you want to determine how much of the given vector field is aligned around this closed loop, That's what you have to determine here. Now see here, what you have to do here, if you want to determine the circulation of vector field around this closed loop, what you have to do, So let us consider this length, from here to here, let us consider this as first line, and this is second one, and this is third one, and this is fourth one. So from here to here you have to determine what? You have to determine F bar dot dl bar. Yes or no? You have to determine how much of the field that is aligned along this length. And similarly you have to determine how much of the field that is aligned along this line. That means here also you have to determine integral F bar dot dl bar. So from here to here also you have to determine integral F bar dot dl bar. So from here to here also you have to determine F bar dot dl bar, right? So if you add up all this here, you are going to get what? You are going to get the circulation of the vector field around this closed loop. Right? Okay. So Neeli Sai Kumar, sir, whether the closed loop dimensions are not negligible or taken in meter square. What here? Whether the closed loop dimensions are negligible or closed loop dimensions. What do you mean by closed loop dimensions here? Loop means it will be in meters or not? Yes or no? Area means it will be meter square. Loop means its units are meters. Yes or no? Okay. See, I am not giving the units for the vector field and all. So I am taking some vector field which is going to have some units. We don't know that units here. Okay, some units. It may represent electric field, or it may represent gravitational field, or whatever it may be. Okay, so it will represent some field, that's it. Understood? It may have any units here. It may represent force field or whatever it may be, right? Okay, so don't worry about the units here. Okay, it is having some units, but along loop you are going to have what? Meters. Yes or no? The units along loop is nothing but meters, right? Okay, fine. So I hope I have cleared your doubt here. Neeli Sai Kumar. Yes, Okay. Now see here. So that means you have to determine f bar dot dl bar along this length plus along this length plus along this length and plus along this length. If you add up all this, you are going to get the circulation of the vector field around this closed loop, right? Okay. Okay, yeah. Now see here. Okay. Now see here. So first I am doing from here to here, from here to here. So that means I am moving along what? X direction, right? Okay. See here. So I am trying to determine the circulation of the vector field around the closed loop. So that is equal to, so first one here, I am moving along this length, Now as I move along this length here, what is varying here? What is varying? Tell me. As I move along this length, what is varying? X is varying, Y is constant. Y value is 0 here, Y is also 0 here. Yes or no? Y is not changing, only X is changing. So you can consider this dl bar, the differential length along X, you can consider it as what here? You can consider it as dx bar. You can consider it as dx bar, or you can simply write it as dx ax cap, right? Now what is f bar here? What is f bar? F bar is going to have x component and y component. So this is x component. So x component is x and y component is what? Y component is y. So always whenever they give the vector field, try to represent the x component separately and y component separately, right? Okay. So this is nothing but x component. F bar is going to have x component as well as what? As well as y component. Now if you do the dot product here, between this f bar and this dx ax cap, what you are going to get here? If you do the dot product with x component, you are going to get ax cap dot ax cap, that is 1. If you do the dot product with y component, you are going to get ay cap dot ax cap, that is equal to 0. Yes or no here? Yes or no? Okay. So first one I am doing, so integral. So I am considering only x component, because if you do the dot product with y component, you are going to get 0. So x component is x dx, you are going to get x dx if you do the dot product. So I hope this one is clear here. Okay. So x dx. Now here x is ranging from where to where here? X is ranging from where to where? From 0 to 1. So x is ranging from 0 to 1. Right. Okay. Plus. Now consider. So I have integrated the function, the given vector field along this length from here to here. Now I am moving from this point to this point here, from this point to this point. In which direction? In y direction. That means this differential length will become what here? Will become dy ay cap. Now this f bar here, is going to have which components here? It is going to have x component as well as what? As well as y component. So if you do the dot product with x component here, if you do the dot product between x component, and this is along ay cap direction. So if you do the dot product between these two, that means x component and ay cap, what you are going to get? 0. Yes or no? Now if you do the dot product between y component and dy ay cap, I can say in this manner. So if you do the dot product between the y component and ay cap, you are going to get what? You are going to get some value, right? So if you do the dot product with x component, you are going to get 0 here, right? So if you do the dot product with y component, that is y ay cap dot dy ay cap, what you are going to get? You are going to get integral. You are going to get integral y dy. You will get integral y dy, right? Okay. Okay, yeah. Next. Now, third one here. See here. Now, as I move, so I have moved from here to here. I have done f bar dot dl bar. Now, from here to here, I am moving in this direction. From here to here, I am moving in this direction. Right. Now here, dl bar will become what here? dl bar will become dx bar. dl bar will become dx bar. Now here you have to consider only what? Only x component here, because if you do the dot product with y component, you are going to get 0. So you have to consider only x component. Now please concentrate here, this third one. See how I am going to write. So integral x component is nothing but what? X. Yes or no? So x ax cap dot dx ax cap. Now see here. Now x is varying from where to where? X is varying from 1 to 0. X is varying from 1 to 0. So x value is varying from 1 to 0. See here, whenever you are doing this integration, most of the students will do it wrongly here, So why means, see here, generally whenever you are doing the integration along this length here, they will consider this dx as what? They will consider this dx as dx into minus ax cap, they will consider. Why means you are moving in negative x direction now. So that's why they will consider this dx as what? They will consider this dx ax cap as minus dx ax cap, because you are moving in negative x direction. That's why they will consider this as dx. They will consider in general this as dx into minus ax cap. That is wrong here. So why means, see here, I will tell the reason. See here, why means, here whenever you are taking the limits here, whenever you are taking the range of x, you are mentioning that you are moving from where to where? You are moving from x equal to 1 to what? X is equal to 1 to x is equal to 0. You are moving from x is equal to 1 to x is equal to 0. Yes or no? You are moving from x is equal to 1 to x is equal to 0. Right? Okay. So here itself, whenever you are representing the range, you are representing from x is equal to, you are moving from x is equal to 1 to what? X is equal to 1 to 0. So that means this range will take care of what here? This range will take care of the direction. So that's why don't include again here minus ax cap. If you include here minus ax cap, and if you take the range from 1 to 0, okay, then you are going to get the wrong result here. So you are including the direction 2 times with respect to range and also with respect to this direction. So 2 times you are including. So both will get nullified and you are going to get some wrong result here. Right. So always consider whenever you are doing the integration along the length by taking the limits or by taking the range, what you have to do is always consider this integration variable as what here? As positive. Always consider this dx ax cap as what here? As positive. And the direction of this one will be taken care by what? Will be taken care by these limits. Okay, so this is very important here. So this is where the students will generally do mistakes while doing the line integration. So I hope it is clear here. Yes or no? Is it clear? Yes. So Neeli Sai Kumar, Hari, Sonu, Dev Sharma, tell me here. Is this clear? Neeli Sai Kumar, what happens if take only one unit vector with negative sign? Which unit vector here? That's what I have explained now. See here, if you consider whenever you are moving in negative x direction, if you consider here dx minus ax cap, suppose you have considered like this, yes or no? And here you are representing in the range also, you are representing that you are moving from 1 to 0, that means in negative x direction. So here you are including the direction, and also here also you are including the direction. So 2 times you are including the direction, that is going to give you what? That is going to give you wrong result. Yes or no? Yes or no? Yeah? Okay, so that's why whenever you are representing the limit from 1 to 0, okay, it will take care of what here? It will take care of the direction. So don't represent here minus and all those things whenever you are representing like this, right? Okay, see, one more thing I want to or you can represent the same thing, or you can represent the same thing in this manner. So don't change the limits here, don't change the limits. So you can write the limits as, see, I can say you can represent the same thing in this manner, you can represent the same thing in this manner. See here, so x is equal to, you can write 0 to 1, and then you can write here x ax cap dot dx minus ax cap. So in this manner also you can write here. Okay, in this manner also you can write. So either you can follow this one or you can follow this one. So my suggestion is always follow this one here, always follow this one. So you are not going to have any confusion if you follow this method, right? Okay. Okay. Next, is it clear here, Neeli Sai Kumar? Yes. Okay. Okay. Now, okay. So now take the integration over this length here, that is do f bar dot dl along this length, that is along negative y direction. So then what you are going to get, that is fourth one here, that is fourth one, what you are going to get, integral. So you are moving along y direction from where to where, from 1 to 0, from 1 to 0. So whenever you are representing 1 to 0, it take care of what, it take care of the direction, it can take care of the direction. That means it is representing you are moving in negative y direction. Yes or no? So here I am representing y is varying from 1 to 0, 1 to 0, right? Okay, now you do the dot product between f bar dot dl bar. Here you are moving along y direction, so this dl bar will become dy ay cap, dy ay cap. So this one here, this one will become what? This one will become f bar dot dy ay cap. Y is ranging from where to where? Where to where? 1 to 0. So this f bar is going to have what? Is going to have x component as well as y component. Only y component is going to give you some non-zero value. If you do the dot product with x component, you are going to get 0. So I am writing here, what is y component here? Y component is y. Yes or no? So you can write simply y ay cap dot what? Dot dy ay cap, dy ay cap. So if you add up all this here, if you add up all this f bar dot dl bar over this 4 lengths here, you are going to get what? You are going to get the circulation of the vector field around this closed loop, around this closed loop. So what is the value you are going to get? Tell me, what is the value you are going to get? Tell me here. So you have to get 0 here, you have to get 0. So check that one here, f bar dot dl bar. So what you are going to get? Tell me. So here integrate, take first section, integrate with respect to x, you are going to get x square by 2, its range is from 0 to 1, plus integral y dy, so that is y square by 2, its range is from where to where? Y is varying from 0 to 1 here. So I have forgot to represent the range. So y is varying from 0 to 1, 0 to 1. So if you integrate this one here, third one, so what you are going to get? X dx, x square by 2. So you are going to get x square by 2. Its range is from where to where here? Its range is from 1 to 0. Its range is from 1 to 0. Right? Okay. Next. Plus integrate this one here. What you are going to get? You are going to get y square by 2. Y square by 2. Its range is from 1 to 0. 1 to 0. Right? Okay. So what you are going to get? Do it here. What you are going to get? You are going to get here 1 by 2 you will get, here also you will get 1 by 2, and here what you are going to get? You are going to get first 0 minus 1 by 2. Here you will get 0 minus 1 by 2. So here minus 1 by 2, minus 1 by 2, plus 1 by 2, plus 1 by 2. So everything will get what? Everything will get cancelled. So this is equal to what? This is equal to 0. This is equal to 0. See, for some type of vector fields, for some vector fields, we can directly tell whether the circulation of the vector field is equal to 0 or not, whether it is equal to 0 or not. We can directly tell here. If suppose if you are having some vector field, you can directly tell whether the circulation of that vector field around that closed loop will become equal to 0 or not equal to 0. That we can directly tell if we study what? If we study Stokes theorem here. If we study Stokes theorem then we can directly tell this one. Okay, we will see that later as we proceed into the subject. We will see this one also. Okay, so that's how I have told the circulation of vector field. For this one you are going to get what? You must get equal to 0. So that is with the help of Stokes theorem I have told that. Okay, so I will explain here later Stokes theorem. So there I will explain how you can directly write whether the circulation of the vector field is equal to 0 or not equal to 0. Okay. Okay here. So now I will give one more problem here. Tell me, you have to tell the answer here for this question. So you have to tell the answer for this question. Now if I give the vector field, f bar is equal to y ax cap plus x ay cap. Then determine the circulation of the vector field. Around the same loop here. Whatever the loop I have given previously, same loop you can consider. So you can consider the same loop here. You can consider the same loop. So this is 0, 0. Let us say this is 1, 0, and this is 1, 1, and this is 0, 1. Okay, so determine the circulation of the vector field. Around this closed loop here. Now the vector field I have given as what? Y ax cap plus x ay cap. So for this one, try to determine the circulation of the vector field around the closed loop. Do it here. Do it. Determine the circulation of the vector field around the closed loop if the vector field is what? Y ax cap plus x ay cap. Okay, do it here. So what you have to do? You have to follow the same procedure here. Right? So you have to determine f bar dot dl bar over this length, and you have to determine f bar dot dl bar over this length, and you have to determine f bar dot dl bar over this length, and f bar dot dl bar over this length. So you have to add up all this. In order to get what? In order to get the circulation of the vector field around this closed loop. See, for this problem you will get not equal to 0 here. So try this one here. Do it. So circulation of f bar dot dl bar is equal to, so integral. So I am taking this first one, 1, 2, 3 and 4. Right? Do it here. So now I am doing directly here. So here this dl bar, here this dl bar is nothing but dx ax cap, and this f bar you have to consider only x component, and here this dl bar is nothing but dy ay cap, and here you have to consider only y component, and here this dl bar is nothing but dx ax cap, and here you have to consider only what? You have to consider only x component, and here you have to consider only y component, and this dl bar is nothing but what? Is nothing but dy ay cap. Now here the range of x is from 0 to 1, here the range of y is from 0 to 1, here the range of x is from 1 to 0, here the range of y is from 1 to 0. Okay, so do it here. What you are going to get? Tell me the answer here. If anybody solve the problem, tell me the answer. So Neeli Sai Kumar, you got 1. Okay, so is there anyone here who got the answer? Please write your answers in chat box here. Right? It is very simple here now. This is x component, right? This is x component, and this is y component. Now do it here. So if you do it from here to here, what you are going to get? So integral x component is y, yes or no? X component is y into dx, yes or no? Y into dx. Now x is ranging from where to where? 0 to 1. Here x component is nothing but what? X component is nothing but y here. Y ax cap dot dx ax cap, you will get what? Y into dx. But as you move along this line here, as you move along this line, what is y value? What is y value? Y is equal to 0 or not? Yes or no here? Along this line, y value is equal to what? Along this line, y value is equal to what? Is equal to 0. And along this line, y is varying and x is constant. Yes or no? Along this line, what is x value? X is equal to 1. And along this line, x is varying, y is constant. That is, this is y equal to 1. Along this line, y value is equal to 1. And along this line here, along this line, what is x value here? X value is equal to 0. X value is equal to 0. Right? Okay. So first one is y dx, x is varying from 0 to 1. Next. Plus, if you integrate along this second line, what you are going to get? So that is fy dot dy ay cap. Y component is nothing but x. So you are going to get x into dy here. So if you integrate along this length here, what you are going to get? So here you have to take the dot product between x component and dx ax cap. So x component is y. So you are going to get y into dx. X is varying from where to where? 1 to 0. So 1 to 0, this will take care of the direction. So don't include minus ax cap and all those things. Yes or no? So I am specifying again the same point here. Right? Next. Plus, if you integrate along this length, what you are going to get? Integral. So here you have to do the dot product between y component and dy ay cap. Y component is x. Okay. So you are going to get x into dy. Y is varying from where to where? Y is varying from 1 to 0. Okay. Okay. So now what you are going to get here? Tell me what you are going to get. See here. Along this first line, y value is equal to what? Y value is equal to 0. Yes or no? So put here y is equal to 0. Right? So this term will become what? You are going to get here 0. Next, whenever you are moving along this line, x value is equal to what? X value is equal to 1. So here y is varying from where to where? Y is varying from 0 to 1 here, 0 to 1. So if you do this integration, x is constant with respect to y. So take x out of the integration and substitute x value. X value is equal to 1. So x value is 1 multiplied by integral dy. Integral dy is y. If you substitute the range, you are going to get 1. 1 into 1 plus. Now here this is third path here. This is along this third path and this is along this fourth path. So along this third path here, whenever you are moving along this line, okay. So what is the value? What is the value of y along this line? Value of y is equal to 1. So now you are integrating with respect to x. So y is constant with respect to x. So take y out of the integration and substitute the value of y. So the value of y is equal to 1. Integral dx here. Integral dx. Yes or no here? Yes. Integral dx is nothing but x. Right? Integral dx is nothing but x here. So if you substitute the range, what you are getting here? What you are getting? X dy, x y 0 to 1. Okay. Next, whenever you are moving along this line, x is varying from 1 to 0. Okay. So y value is equal to 1. So integral dx, if you substitute, the range of x is from 1 to 0. So substitute here, what you are going to get? 0 minus 1, right? Plus here along this length x value is equal to what here? So x is constant with respect to y. So you will get integral x integral dy. So y is equal to 1 to 0, but x value is equal to what? Along this line, x value is equal to 0. Okay, so this term will also become 0, right? So what you are going to get here finally? So for this one also you are getting what? Here you are getting 1 and here you are getting minus 1. So you are getting what? You are getting 0 here. So for this problem also you are getting the circulation of the vector field around the closed loop is equal to 0. So please check once here calculation. Please check once the calculation here. Is it correct? Everybody got the same answer here? Please check the calculation once and let me know whether you also got the same answer or not. Tell me here. Okay. Yes or no here? Everybody got the same answer? Yes? Sai Kumar, Dev Sharma. Tell me here. You got some different answer or same answer? Tell me. Check the calculation and let me know whether it is correct or wrong. I am waiting for your response here. Yes? Yes, yes. No, what I am asking is everybody got the same answer, 0. Right? Okay. So this is all about circulation of vector field around any closed loop here. Circulation of vector field around any closed loop. So they will give some vector field and they may ask to determine how much of that vector field is aligned around the given closed loop. Then you have to determine circulation of the vector field around that closed loop in this manner. You have to integrate f bar dot dl bar throughout the closed loop. Yes. Okay. So everybody got the same answer, right? Okay, fine then. Okay. So this is all about circulation of the vector field around any closed loop, right? Okay. So if you have understood this circulation of vector field, clearly, then you can go for what here? Next we can go for curl here. Okay. So just I will give you the mathematical expression for curl here. So next we can go for curl. Right. Okay. So mathematically, how to represent curl here? So we can represent curl mathematically in this manner. So del cross f bar is equal to what? So we can write the curl in determinant form. Yes or no? In determinant form in this manner. So I hope you know how to write in determinant form. Yes or no? So here ax cap, ay cap and az cap. So here dou by dou x, dou by dou y, dou by dou z, and here fx, and here fy, and here fz. Okay. So if you expand this, what you are going to get here? You are going to get ax cap. You are going to get ax cap into dou fz by dou y minus dou fy by dou z, right? Minus ay cap into minus ay cap into minus ay cap into, you are going to get dou fz by dou x minus dou fx by dou z, right, plus az cap into dou fy by dou x minus what, minus dou fx by dou y. So this is the mathematical representation of curl here. This is the mathematical representation of curl. Okay. So now I will tell you how to write this curl directly. So without expanding, every time it is not possible to expand this curl and write in this manner here. So instead we can easily, I will tell you a method to write easily this curl here, to expand this curl easily. Okay. So that is, see here, how I can write that. See, what you have to do is, so whenever you are expanding curl, write in this manner here, curl of f bar, del cross f bar is equal to, so first you write here x component, that is ax cap, x component, that is ax cap. So whenever you are writing x component here, see, always follow this one here. So x to y to z. Okay, so first you have to get x, after that y, after that z. If you are having y, then you have to follow z, then x. Right, if you are having first if you are seeing z, then you have to follow x and then after that y. Okay, so follow this order here, Now here you are having what, you are having a x cap, you are having here a x. Okay, so next what you have to do is differentiate here with respect to what, here you are having x, so differentiate here with respect to y, right. So minus, and then after y, x is completed, y is completed, after y you are going to get what, z. Okay, so dou by dou z. Okay, so whenever you are writing the x component here, you have to differentiate the y components and z components. Whenever you are writing x component of curl, you have to differentiate y components and z components. You have to differentiate the y component with respect to z and differentiate the z component with respect to y. Yes or no? Okay, so here you have to differentiate the z component with respect to what, z component with respect to y and y component with respect to z. So x component of curl is completed. So how you have written, here you have written x component, that is x here, then y here, then z here. So now differentiate the z component of the vector field with respect to y and y component of vector field with respect to z. Okay, so in this manner you have to write here. So next plus ax cap here, plus ay cap, write it as plus ay cap, right. Okay, so next what you have to write here, tell me what you have to write, So here you are having y, so after y, next what you have to see, z. Yes or no? So here differentiate with respect to what, z here, minus after z what you have to get, x. So differentiate with respect to x, here differentiate with respect to x, right. Now what you have to do, so differentiate the x component with respect to z and z component with respect to x. So you have to differentiate the x component of vector field with respect to z and z component of vector field with respect to x. So y, z, x. So in this manner you can write here, So next similarly plus az cap, Now if you see here, you are having here y, here z and x. So y started from y, then z and then x, right. So differentiate always x component with respect to z and z component with respect to x while writing the y component. So with this we have completed the y component here. Next, how to write the z component, Now here you are having z, So next what you have to write here, dou by dou x. So after z you are having what, x. Yes or no? Dou by dou x minus what, dou by dou y. After x you must get y here. So here z and here x and here y. Now differentiate the y component with respect to x and x component with respect to y. Okay. So differentiate the y component with respect to x and differentiate x component with respect to what? With respect to x. So in this manner you can directly write here. In this manner you can directly write the expression for what? Expression for curl here. Okay. See, if you observe this one and this one, this one and this one, both are same here. Here you have written minus ay cap. Here you have written minus ay cap into dou fz by dou x minus dou fx by dou z. But here how you have written plus ay cap into what? Dou fx by dou z minus dou fz by dou x. So both these terms, y component terms here and here, both are what? Both are same. Yes or no? If you multiply with minus here, you are going to get the same term here, same term. So in this manner you can write what? You can write directly curl of f bar. Okay. So just practice, for practice, just finally you can write how to write. So you can write fastly here. See here. So del cross f bar is equal to what? Ax cap. So here you are having x. So differentiate with respect to y and differentiate with respect to z, right? Okay. Now here you have to differentiate the z component with respect to y component with respect to z, plus ax cap, Here you are having x. Next you have to differentiate with respect to y, differentiate with respect to z. Now here you have to differentiate the z component with respect to y and y component with respect to z, plus az cap. So after z you have to differentiate with respect to x minus differentiate with respect to y. So differentiate the y component with respect to x and x component with respect to y. So in this manner you can directly write here. So there is no need to write that determinant form and all every time. Okay. So you can directly write the expression in this manner. So is it clear here? Yes or no? Yes. Dev Sharma got it. Okay, fine. Yes. I hope it is clear here. I hope it is crystal clear. Okay. Okay. Now, see, if I consider the vector field here, just I will give one simple trick here. If you consider the vector field, if you are having the vector field like x component is a function of only x, if you are having x component is a function of only x, plus if you are having the y component which is a function of only y, and if you are having a z component which is a function of only z, if you are having the vector field in this manner, then tell me what is the curl of this type of vector field. What is the curl of this vector field here? Let us say this is f1. f1 bar is equal to, it is having x component, y component and z component. X component, if x component of the vector field is a function of only x and y component of the vector field is a function of only y, then z component of a vector field is only a function of z. Then in that case, what is del cross f here? What you are going to get? Tell me. What you are going to get? What is del cross f? If x component is a function of only x, y component is a function of only y, z component is a function of only z, then what is the curl you are going to get? Tell me here. Which one here? Neeli Sai Kumar, second term is wrong. Which one here? Which one is wrong here? This one. Oh, okay. Fine. So I have to write here ay cap na. Okay, thank you. So here you have to write ay cap. So here it must be dou z and here it must be dou x. So yes here. Thank you, Sai Kumar. So whenever we are in flow now, sometimes it happens here. Okay. So y, z and here x, right? Now here you have to differentiate. With respect to what? You have to differentiate the x component with respect to z and here z component with respect to x, right? Now is it okay here? Rohit Kumar, yes, 0. Yes, you are correct. Now Sai Kumar, I have corrected that one. Is it fine? Okay. Okay. So what you are going to get for this vector field? For this vector field, you are going to get what? You will get always equal to what? Always equal to 0. Always equal to 0. So y means see here, whenever if you observe this curl expression here, if you observe this curl expression, what you are doing here? What you are doing here? You are having z component. Here you are having z component, and here also you are having z component. So here you are having z component, and here also you are having z component. So the z component of vector field you are differentiating with respect to what? With respect to y and with respect to x. You are not at all differentiating the z component with respect to z while doing curl. Yes or no here? So if fz is a function of only z, now while expanding curl you are differentiating the z component only with respect to y and x. You are not differentiating this component with respect to z. So you are going to get what? So this term will become 0. This term will also become 0. Right. Now if you consider y component as a function of only y, now if you observe here, you are differentiating the y component here with respect to z, and here you are differentiating the y component with respect to what? With respect to x. Now if you consider y component as a function of only y, then this term will go to 0, this term will also go to 0. So already we got this term 0, this term will also go to 0. Now this term will go to 0, and this term will also go to 0. Now if you consider x component as a function of only x, if you observe, you are differentiating the x component with respect to what? Z, and here also you are differentiating the x component with respect to what? With respect to y. So if you consider x component is a function of only x, then differentiation with respect to z will give you what? Will give you 0, and differentiation with respect to y will also give you what? Will also give you 0. So all the terms will go to 0 if x component is a function of only x, y component is a function of only y, z component is a function of only z. So in that case you can directly write the curl of f bar is equal to 0. So for this type of fields here, for this type of fields, always for this type of fields, always you can directly write curl of f bar is equal to what? Curl of f bar is equal to 0. Curl of f bar is equal to 0. Right? Okay. Okay. So I hope it is crystal clear here. I hope it is crystal clear. So this is the mathematical expression and how to expand this curl, and all these things we have discussed here. So next we will discuss about the physical interpretation here. Next we will discuss about the physical interpretation of curl. So what actually this curl represents? What is its physical interpretation? So next we are going to study about the physical interpretation of curl here. So once we understand the physical interpretation of curl, then we will study about Stokes theorem. Right? Okay. So for today's class, I am winding up the session with this here. So tomorrow we will see the physical interpretation of curl. So what actually curl means? So I will take some different examples to explain the physical interpretation of curl, so that you are going to get very much clarity about curl, what actually curl means. Okay. So that's what we are going to discuss tomorrow here. Just I have explained how to write this curl mathematically. Understood? And which type of functions the curl will become 0. So those things we have discussed here. See, I am not saying only this type of functions are going to get curl equal to 0. There are many other functions for which curl will become equal to 0. But if you see the field in this manner, then definitely for this type of field the curl must be 0. Okay, so that's what I am specifying here. Right? Okay, so I hope it is crystal clear here. So in the next session we will see the physical interpretation of curl here. Right? Okay. Neeli Sai Kumar. Sir, shall we say curl is an example of cyclone? I will explain here. The physical interpretation tomorrow here. Tomorrow I will explain everything. Right? Okay. So as far as today class is concerned, so I am winding up the session with this, and tomorrow we will see the physical interpretation of curl, and also if possible we will start Stokes theorem here. Okay, so I hope you have enjoyed the session. So if you are having any doubts, you can ask me here, otherwise we can wind up the session. Yes. So is everything clear here? Is everything clear? Yes or no here? Is everything crystal clear? Yes. Dev Sharma, can we get previous classes on the YouTube? Yes, here it is available in our GATE Academy Global channel. All the lectures are available here. All the lectures are available. You can type go to GATE Academy Global channel. There you can type EMT classes by Karthik sir or something like that. You are going to get all those videos. You are going to get all those videos. Okay. So Neeli Sai Kumar, thank you sir. We enjoyed a lot. Thank you dear. Thank you. So okay here. So share this session here. Share the session to as many students as possible. So if we get more number of students in live now, we can plan many more sessions like this, right? Okay, so depending upon your response we will proceed here. So that's why share the session to as many students as possible, so that we will plan some more sessions also. Okay, yes Dev Sharma, that's what I am saying. You will get the previous classes also. Yes, it is there in GATE Academy Global channel. You can search. You can search with my name. Okay. Okay. Okay here. So with this I am winding up the session. So tomorrow we will meet guys. Don't miss tomorrow's class. We are going to see the physical interpretation of curl, which is very important and which is very interesting. I am going to take some interesting examples to teach this. Okay, so don't miss the class tomorrow. So tomorrow exactly at 4 p.m. here. Tomorrow exactly at 4 p.m. at the same timing we are going to start the session here. Okay, so don't miss the class and share this session to as many students as possible, so that everybody will get benefited here. Okay, so thank you guys. So we'll meet tomorrow exactly at the same time 4 p.m. So until then, take care. Bye bye.